Welcome everybody. My name is Ramon Amela and I'm research engineer at Rootstock Labs. And I'll be presenting the treasure hunting mistakes on Bitcoin, or how two different parties can trigger a protocol to look at a chain of hashes and see the step that contains a disagreement between them so we can verify a computation on chain. We'll start with a little outline, saying the Bitcoin context that makes this necessary, a little recap of the technologies that have opened the door to do this, and we'll end up with a little hands-on performing an area research on chain. So, regarding the context, Bitcoin scripts are completely stateless. They have a very limited number of opcodes. There's no transaction introspection, and the sign arithmetic operations are with at most 32 bits. This makes the expressivity of Bitcoin scripts very limited, and there are some ways that we can soften these limitations by using these components. So I'll start explaining what are connectors, Winternitz one-time signatures, and chain hashes. So at the end, we can use all these concepts to perform a search in these hashed chains. First of all, let's see what's a connector. So basically, when we build the transactions, we can build them and sign them before they are published. So we can create a chain as follows. So we have transaction A, followed by transaction B, followed by transaction C. And we have to take into account that we cannot publish the second one before the previous one is published in the blockchain. The main advantage is that when we can build this because the addresses are actually computed knowing the public keys or the pay-to-script hash, SegWit, or Taproot. We'll focus on Taproot since it's the one that gives more expressivity, and knowing the script that we want to verify, we can build the address, then build all the transactions, and build this kind of schemes. Keep in mind that in this schema, C cannot be published until B is in the blockchain, and B cannot be published until A is in the blockchain. Once we know this, we can think on having more complicated schemas. We could think on this schema here, where transaction C not only have one input, but has two different inputs. And until both A and B are not in the blockchain, we cannot broadcast transaction C to be included in the blockchain. In a similar way, we can think on a schema where we have transaction A1 that is previous to transaction B and transaction A2 that is previous to transaction C. But if we look at how the transactions have been built, we can realize that both of them are consuming the same transaction and index in the previous transaction. What does it mean? That we could change this schema and saying that from this original transaction, we can go to either transaction B or transaction C. But not the two of them can be published since they are consuming the same input at the beginning. So afterwards, if A1 is published, A2 cannot be published, so we are in this scenario here. In the other way around, if we publish the one that ends up in transaction C, the path going through transaction B is deprecated. So mixing these two different concepts, we can express dependencies and mutually exclusive paths, having really complicated graphs through the network. We can do this just by pre-signing all the transactions, so we are sure that none of the parties participating in the protocol is able to modify it to get the funds afterwards. The next important context are Winternitz one-time signatures. The base of these signatures is to give a pre-image that once we hash it a determinate number of times will give us a certain value. So the only way we can publish, in this case, the hash value 2 is to know the pre-image that once it's hashed one time will end up giving us the hash value 3. So we can think on this as like, give me a pre-image that once is hashed 3 times will give you this public key. Or give me another pre-image that once is hashed 1 time will give this public key. This means that with the same public key, we can encode as many values as many times we are hashing these pre-images. The main disadvantage of this is that once we are showing, in this case, the private key 2, since we are hashing them several times to get to the public key, we are automatically revealing the private key 1 and private key 0, since these private keys can be obtained by hashing the first private key. To avoid equivocation, so people can change the value that we just published, there's a checksum that is added. You can look a little bit more on how this checksum works. But I wanted to explain this because afterwards, when we publish these values, you'll see that there's a value. The value published, that is the actual one that we want to publish, and something that goes next to it to avoid this equivocation. And once we get to this step, since one party has all the private keys, there's nothing that forces them to always have the same value. So this party could keep changing this value all the time. And to avoid this, we have 2 mechanisms. That is, in the graph that we described before, we could add a path where if the other party holds 2 different values for the same public key, we slash the funds and we end up the protocol. This would be one way to do it, but the other way is to force the other parties to reassign the values that we are broadcasting. So if, for example, one party is broadcasting a 1, the other party can reassign it, and then when the first party needs to reuse this value, instead of reusing its own private public key, will reuse the one from the other party, and since the first party don't have the private key of the second one, is no longer able to change this value. And finally, we'll define what is a hashed array. A hashed array is, let's say that we have an original array of values that is expressed like follows, so value 1, value 2, until value n. We can define a first step that we will consider a nonce, expressed as hashed array minus 1 equals c, and then each one of the positions of the hashed array will be composed of the hash of the previous hash and the value of this position. This trick means that for the fact that we are just chaining all the hash, if we agree that the value is correct for one position, we can assume that the value in this position on the original array and all the previous ones are the same ones for both parties. But what does contain the first value array? So it can contain transactions. This would be the case of Bitcoin. So when we hash the header considering the previous hash, we are agreeing that all the previous blocks have the same content for the 2 parties that are looking at the headers. It can be computation steps, like in BitVMX or all these frameworks that are arising lately. And it can be anything that can be vectorized, that it has not been invented, but maybe in the next times, there's somebody that comes up with a different protocol. So once we have the hashed array, the goal here is to find the discrepancies. And I'm going to explain now how to efficiently compare 2 arrays, or 2 hashed arrays, and find the step that is putting a mistake in the hash arrays. So how does it work? First of all, the first party that wants to prove that is able to execute this computation will publish the last array. Then anyone that knows how to obtain this array can compute all the values of the array and compare the last hash to the one that has been published. If these 2 hashes are equal from the property that we obtain with the chained hashes, we can ensure that all the computation is the same for all the parties that are looking at this hash. Nevertheless, if we look at the hash and it is different, we can say for sure that at some point, both arrays have diverged. So in case of the disagreement, we can keep publishing intermediate results, so we end up knowing which one of these steps was the wrong one. So putting this as a simple example, we could imagine a computation of 16 values and express this as a tree. So at each step, we reveal intermediate results that will allow us to know which one of the intervals contains this discrepancy. When we define the protocol, though, we need to know exactly the length of the final array. How do we do that? First of all, we define how many intervals there will be at each one of the steps. Then we say we define how many iterations we'll perform to find this wrong step. And finally, we can say that the vector length will be n to the q. There's an interesting property that says that if we fix n equal to a power of 2, as we are choosing the intervals, we'll be broadcasting the exact step where this has been mistaken. So in this case, we come from the previous example, and we'll assume that the first step that is wrong is the sixth one. In here, you see all the values that can be chosen at each time. So once the intervals have been chosen, we can choose one of the intervals, and depending on the interval that we have chosen, we'll show one value or the other. In this case, the prover, the one that wants to demonstrate that this computation has been done and has been done correctly, will broadcast the 15. Then, considering that the sixth one is the first that is wrong, we assume that publishing the 3, the 7, and the 11, an external observer can see that the 3 is correct, but the 7, in the 7, there's already a discrepancy. When the other party sees that, publish the 1 to specify which one of the intervals is the one that we want to explore, and once this is done, the prover shows the steps 4, 5, and 6. So at this point, the external observer can see the 4, 5, and 6 and realize that the first one that was wrong was the 6th one, and it published the 3 here, the 1, 0. We can see here the order in which each one of these things have been published. So first of all, we have the 15, the protocol gets triggered, we show the first intervals, then we choose one of the intervals, we show yet another row of values, and finally we find the first one that is wrong. And now I'm going to show how to actually implement this on Bitcoin. To do so, we'll imagine a setup here between Alice and Bob. Alice will be the one that is trying to prove this value, and Bob the one that is challenging it. So, as we said, all this is a protocol that is formed by change transactions, and all this protocol needs to be pre-signed in advance, so we are sure that any of them is able to change the path that we are following. So we're going to follow these two different Jupyter notebooks that don't see one to each other. So we start importing everything. Then each one of the parties will define its private keys. That many private keys are not necessary, but it was more clear for me when I was building the code. Each one of the parties computes its public keys. Then we define the setup parameters. Since we are implementing the case I just presented before, here, for example, we have that at each revelation we'll show 3 different values. Here, we specify in which the amount of bits that will contain in each one of the words that are shared. So if, for example, here we are showing 2 bytes, but the bytes are chunked in 4 bits, 4 bits, 4 bits, 4 bits. And if, for example, we want to show 20 bytes, we could just show 40 words of 4 bits. So this is not a limiting fact, I would say. It's just a configuration one. Then each one of the parties computes all its public Winternitz keys. And at this point, in order to build the scripts for the protocol, the 2 parties need to exchange the public keys for the Winternitz signatures so they can actually build the scripts. So here I did a little trick. We just print it. And we could imagine that at this step, they are exchanging this information. Just copy from one side to the other. And here we have Alice that sends all the public keys to Bob. Once they have the public keys for the Winternitz signatures of the other party, they can continue by building all the scripts that will verify the signatures that we described before. So at each one of the steps, they will be verifying that the value that is posted on chain is correct, and it holds the public key that they have exchanged. And before we start building the addresses, we need to fund the first script. To do so, we'll use this multi-net testnet that is just a regular Bitcoin testnet, but that has confirmation blocks every 30 seconds, which is really convenient for a demo. Now we send the funds, and we just wait until the funds are here. So now that we have the transaction ID, we could come here and just verify that the block is indeed here. Now it's confirmed and has this amount here. So now we just need to compute which is the exact transaction and the index where this has been logged. We exchange it. So now both parties have the same origin, let's say, and they can start building all the addresses that are related of each one of the scripts that form the protocol. So we have Alice with all the scripts here, and Bob with the same scripts. Now that all the addresses are constructed, we can start building the actual transactions. Once again, they will, on each one of their sides, build all the transactions and generate signatures for these transactions. The important thing here is that each one of the parties has its private key. They will sign all the transactions, and since they are signing the transactions, the other party will not be able to sign them to change these transactions or to change the destination of the funds, since we force the verification of both transactions at each one of the scripts. Once this has been done, they need to exchange the signatures, so each one of the parties will be able to afterwards publish message on chain. This is the second time they are exchanging information, so just in summary, they have started sharing the Winternitz public keys, and then they share the signatures. Once we are here, everything has been constructed, and we can imagine that we are in this case here. Alice is trying to prove that this is correct, but Bob realizes all the computations internally and sees that the hashes are these ones. As we see in the 6th step here, there's a discrepancy, so we'll try to use the blockchain and all this schema and protocol to find the first step that was wrong. So the first thing that Alice do is, as we said, publish the last hash. So we'll see it here. We execute this. We obtain the transaction. And we broadcast it. If we inspect this transaction here, and we go to details, we can see that we see this F, 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 F with all the corresponding private keys. And in addition, these two items here are the ones that I was saying before, that are the checksum. That is what will force the other party to publish exactly the same value and don't allow them to change it. Here we see the two signatures and the script. Once this has been done, Bob can look at this exam message and say, okay, I see that the hash that has been published is the FFFF. I disagree, so I will trigger the protocol. So he publishes the next transaction here, just forcing Alice to unveil more hashes. So at this step, Alice is forced to show the first row in the diagram that we had before, and in this case will be 3, 7, and BB. So we execute this, we come here, and we broadcast it again. Once again, we can open it. So Bob, because this is public, this is not in my computer, it's in the real blockchain, we can see all the values here, the B with the checksum, the 7 with the checksum, and the 3 with the checksum. So Bob can say, okay, the first value is correct, but the second one is not. So now I will choose which path, which interval is the one that should follow. And he will just broadcast all these values here. I don't know if this has been correctly copied. Yeah, it seems so. So now Alice, once again, here they are not exchanging information between them with any mechanism other than the blockchain, indeed. We can come here and see this interval with the checksum, so finally Alice can unveil the values 4, 5, 6. And since we are looking for the correct step, what could happen is that Bob afterwards says, no, in fact, I didn't ask for the value 1, I asked for the value 2. So just to avoid this equivocation, what Alice is doing is, if we come here to the details, she will broadcast the 6 here, then the 6 with the checksums, the 5 with the checksums, the 4 with the checksums, and at the end, she will broadcast the original value Bob has selected in the previous step and resign it with its own keys. This way, we can use this value afterwards, since on the one side, Bob signed it the first time, and then Alice resigned it so Bob can reuse it. Once Bob sees this, he can come here and indeed broadcast this value here. And if we inspect the transaction, he now published the new step, that's the 2, more the previous one that he had broadcasted, but now instead of using its own private keys, he's using the private keys that were broadcasted by Alice. By using these 2 values, in this Bitcoin script, we are able to compose these 2 values, and the 0102 gives us the number 6. That's corresponding to the first wrong step. And with that, we just follow a whole protocol that allowed us to compare the chain hashes of both parties. And this is how basically we can build a research on blockchain. So I don't know if there are questions. Okay, so they are asking how many bytes per bit exchange we are exchanging. So for the Winternitz signatures, as of now, if I remember it correctly, we are between 20 and 25 bits per bit shared. So yeah, the factor is pretty high, but nonetheless, it's what allows us to have a stateful protocol inside the blockchain where 2 parties are just able to interchange messages just looking at what's being published publicly. Okay, so.